have relativity. Okay, then we have special relativity in 4-vector notation, 4-vector or tensor notation. Okay, then we have free particle, free relativistic particle, dynamics of free relativistic particle. Then we considered charged relativistic charged particle, in electromagnetic field. Okay, then we discussed we discussed how to get Lorentz force law and everything in the covariant notation. Then we discussed Maxwell equation in covariant form. Okay, so this is what, so our status is this now. Okay, so we are at this stage. Okay, so the Maxwell equation, okay, is by construction they respect the laws of special relativity. Okay, on the other hand, your Newtonian mechanics do not respect the laws of special relativity. Okay, Maxwell equation, they do respect the laws of special relativity. Okay, so there is no such a thing called non-relativistic limit of Maxwell equation. Okay, you can discuss electrostatic, you can discuss special cases, but there is no such a thing called non-relativistic limit of Maxwell's equation. Maxwell equation in they already in the there is no clash between special relativity and Maxwell's equation. Okay, in fact, your Maxwell's equations were played pivoting role, okay, in developing the special relativity. Okay, we have just written the Maxwell equation in manifestly covariant form. Covariant form, I mean the manifestly covariant form. But Maxwell equations, even if you don't use covariant form, okay, if you use your usual vectorial del cross E, del cross B, and so thing, they respect the laws of special relativity. Okay, so there is no problem at all. We wrote that in manifestly covariant. Okay, so Maxwell equation represents, it is actually the first non-trivial relativistic system which is observed in nature. Okay, first non-trivial relativistic system which is observed in nature. Okay, and using the Maxwell equation in covariant form, okay, you can also write down the wave equation. Although I have not derived that the equation satisfied by mu is actually same as wave equation, but one can do that. So the wave equation, okay, for vector potential mu. Okay, so this is the byproduct of your Maxwell's equation. Okay, so this represents your first non-trivial relativistic system, okay, which is observed in nature. Now the question is, now we want to discuss the quantum mechanics for relativistic particles. Okay, so that is our aim, the quantum mechanics for relativistic particles. That means I need to first thing is to construct an equivalent equation of Schrodinger-like equation which respects the laws of relativity. That is the first thing. Okay, and in that equation, your dependent variable, okay, in that that will be differential equation. Okay, in that differential equation, your dependent variable will be designated as wave function. That is what you do. Okay, you have a Schrodinger equation, and the dependent variable, which is psi, in that case, was interpreted as wave function. It is actually wave function. So now I want Schrodinger-like differential equation which respects the laws of special relativity. Okay. Now I am not going to discuss the. Now this is not true. Okay. Now we are not discussing the dynamics of relativistic free particles and so on. Okay. This is not what we are discussing. Okay. So you always remember. So you have Newtonian mechanics. You have F equal to ma. Okay. Then you go to quantum mechanics. You don't bother about this equation. You consider this rule, right? Okay, this is not F equal to ma equation. Okay, this equation will tell you the dynamics of what is known as this wave function. This wave function is used to calculate the expectations value of classical observables. Okay, when you calculate the expectation value of observable, you have to calculate in some state. Okay, that state will be given by Schrodinger equation. Okay. Now, similarly, we have here relativistic equation for free particles. Okay. Now, what should be the differential equation for the quantum mechanical wave function in this case? Okay. So, what we have here. Okay. So now let us start with that. So our goal is to propose the equation describing relativistic quantum particle. And note that we are discussing about the particle, not electromagnetic field. Okay. It is just like what we did in quantum 1. Okay. And first we will so with mass. So this particle means with mass. Okay. So this is our goal. Okay. So in our system, what we have since we are discussing about we are introducing quantum effects or quantum mechanics. So I will be having H cross. Then I have relativistic. Okay, that means I will have C. Okay, then obviously I will have mass also. But mass is not your constant. Okay, it is one can consider it is a parameter. It's not a constant in the sense that these are universal constants. Okay? I can consider relativistic quantum particle of any mass, right? So in that sense, m is not really the constant here. So I have H cross and I have C. These are the constants which are there in our system. Okay, nothing else. Right? Yes, relativity means you have C, and quantum means you have H cross. Okay. Now another thing which we need, I need to highlight is that, okay, any relativistic generalization of Schrodinger equation must have same order of time and space derivative that we discussed. Okay. So is this clear? This statement I discussed briefly last time. Okay. Any relativistic generalization of Schrodinger equation must have same order of time as well as space derivative. So if you want, if there is first order derivative in time, then for its relativistic generalization must have first derivative in space, first order derivative. If it is on the other hand, if I have second order derivative in space, then I must have second order derivative in time. Okay. And thirdly, since we are discussing relativistic particle, it must obey E square E equal to, this must be satisfied, E equal to P square C square plus M square C to the power 4. Okay. So this is the energy of relativistic particle. Okay. So these are our guidelines. Okay. In fact, this is not a guideline, but these two we will use to construct the relativistic generalization of Schrodinger equation. And after doing this, we should have correct non-relativistic limit. Okay, non-relativistic limit. Okay. So now recall what is non-relativistic limit. In the non-relativistic limit, okay, your E minus rest energy, say E0, okay, must be much smaller than E0. Okay, that is our non-relativistic limit. Okay. So your kinetic energy must be much smaller than your rest energy. Is this clear? Okay. So now let us. So the first thing we will consider is Klein-Gordon equation. As we will see that the Klein-Gordon equation describes relativistic generalization of Schrodinger equation, but this Klein-Gordon equation is appropriate for a particle having no spin. Okay? So it is suitable or it is appropriate for spinless relativistic quantum particles. We will see that. So how to construct? So I will use these two criteria. Okay. So suppose, let us consider first this equation. Okay. You have E equal to square root P square C square plus M square C to the power 4. Okay. Now I will use what is known as correspondence principle. Okay, what is correspondence principle? You say that the observables in classical mechanics, if A is observable, then it is elevated to operator. Okay, so observables in classical mechanics, they are now elevated to operator in quantum mechanics. So this is classical and this is quantum. Okay, so for energy, what you use? Energy, the correspondence is energy will go to I h cross del del T. Okay. Your quantum 1 and your momentum is minus I h cross gradient. Okay, clear? Now here what I will do, okay, so here we have in relativistic case, we have P0, which is E by C. Okay, so this will be replaced by I h cross by C del del T, which is nothing but I h cross del 0. It is same as I h cross del 0. Okay, and your P spatial momenta will be minus IH cross gradient. Okay, this will be, in our notation, this will be minus IH cross del I. Okay, so your P mu will be replaced, a classical P mu will be replaced by IH cross del 0 and minus IH cross del I. Okay. Is that fine? So now if I replace this here, okay, if I substitute this naively, if I substitute these expressions here, what I am going to get? I will get IH cross del T as a, I will write this as an operator equation. IH cross del T equal to square root. Okay. So we will have H cross square grad square plus H square minus H cross square grad square, this is Laplacian square, plus m square c to the power 4. Okay, and since this is the operator equation, this means there is an identity. Okay, is this clear? So this is what we have. Okay, but obviously this, I cannot use this as my wave equation. So suppose if I say that if I construct naively, if I construct a differential equation from that, that means I will consider a wave function psi, okay, is a function of x and t, okay, and I will operate this on this psi. So del psi by del t, okay, del psi. So I should have here c here, okay. So P0. So as far as E is concerned, this is just IH cross del T equal to this square root. I will have this square root. And this will act on this side. Okay. But you will see that I have square root here. So square root of some operator, say A, plus some B. Okay. So if I expand this square root, I will have all the orders of A. Right? I am not bothering about B because B in our case is just this. Okay. So if I expand this square root, that means I will, in that expansion, all the orders of A will be there. I will have A square, A cube, etc. Right? Okay. And all those will act on psi. So as a result, I will get nonsensical differential equation. Okay. So left hand side you have first order. It's not nonsensical, but I will definitely I will not have same order of space and time. Right? Because on the right hand side we have, if I expand this square root, then I will have all the orders of this derivative. So it's starting from square, fourth power, sixth power, and so on. Okay. So this is not a nice way of generalizing your Schrodinger equation. Instead of that, what I could have done? Instead of that, okay, I consider the following relation. I consider this. I will use E square. I will square the classical energy equation. E square equal to P square C square plus M square P to the power 4. And now if I replace, okay, now if I replace, now if I use this correspondence principle, then I will get, minus H cross square del 2 by del t square psi, okay, equal to minus h cross square Laplacian square, okay, plus m square e to the power 4 psi. So this is what I get, and now I have same order of time and space derivative. But see, it's not easy step. See what I have done. I am now considering the squared equation. That means if I want to get my energy from this, that energy will have two signs. Correct? Okay. Because then E will be plus or minus this relation. I have to consider two signs, both the signs, plus as well as minus. We will see that. So is this step clear? So I will just rearrange this.
Yes, sir.
Okay. So it will be minus h cross square. I will just rearrange this del 2 by del t square. Okay, and I will bring this on the left hand side. I will bring the RHS to the left hand side, and I will get plus h cross square Laplacian square minus m square e to the power 4 acting on psi equal to 0. Okay. So I will get, if I take minus sign common and if I divide h cross, then I will get del 2 by del t square, okay, minus Laplacian square. Okay. So I will get minus Laplacian square, but minus of Laplacian square is nothing but minus of del I is nothing but plus del I. Okay, now you are comfortable with this. So I will get del 2 by del t square, okay, plus del I, okay, minus mc divided by h cross square acting on psi equal to 0. Okay. And sorry, there is a mc to the power 4, so I should write here c square here. So there m square m there is m. So let me write it. Yeah, this is correct. Just a minute. There should not be any factor missing. Yeah. So c square. So this c square is there here. Sorry, this is c square. Now I will divide by c square. So if I divide by c square, then it will be 1 over c square del 2 by del t square. So that will be del 2 by del x0 square. Okay. Because this c square will go del I, okay, minus mc divided by h cross whole square psi equal to 0. Okay, and that is nothing but del mu minus m minus this plus sign. Okay, it will be minus here. So when I change this sign, there should be plus sign here. Should be plus sign here. Okay, so there is a plus sign here. mc by h cross square psi equal to 0, which is also written as box plus mc by h cross whole square acting on psi equal to 0. And this is your Klein body. Okay. Right. So this is the generalization of your This is one of the generalization of your one way to generalize the Schrodinger equation. And here psi, we want to interpret this psi of Tx, we want to interpret this as wave function. Treat this as wave function. Okay, fine. So now instead of I h cross del psi by del t equal to h psi, I have in the relativistic domain, I have box plus mp by h cross square psi equal to 0. In fact, h I can write as your minus h cross over 2m Laplacian square plus v of x psi. Okay. So if you consider free non-relativistic quantum particles, then v is 0. So it will be just minus h cross square upon 2m del square. So maybe I should write here h cross del t minus it will be plus h cross square over 2m okay. So this is the generalization to this is the relativistic generalization of Schrodinger. Okay. Any question so far? Any question, comment? So here we chose the root within which the spatial derivatives are at second order spatial derivatives, and the time the order of time derivative is also second order. Okay. So we raise the order of time derivative. As a result, you expect that raising will lead to e square, not e. Correct? Because of it is second order in time. Okay. If I consider the stationary solutions at this step, okay, then I will, if I act this time derivative on this factor, okay, I will get, since there are two time derivatives, I will get e square. Okay. So this equation is consistent with this. So the energy of that particle will be plus or minus square root of this. Energy of the quantum particle will be plus or minus square root of this. We'll see that. Okay. So this is actually the free Klein-Gordon equation, because this is energies of free relativistic particles. So our starting point was this. So remember, this is not the derivation of Klein-Gordon equation. It's not at all a derivation. It's just a guesswork. We started with this. Okay, we use the correspondence principle and we arrived at this. So it's not really a derivation of relativistic free equation. You know that Schrodinger equation also is not a derived equation. It is a guessed equation. Okay. Is that clear? So let us see what we can do after this. Okay. So let us try to interpret what this psi may be. What this psi? what is the interpretation of this psi? Okay. So suppose if I multiply this relation, okay, or if I multiply, so I will, maybe we can use also frequently, I will use this relation. So if I consider, if I multiply this equation from the left by psi star, see, psi is a function, it could be complex, it could be real. But let us consider, let us keep it general, okay? Then it will be a complex quantity. Okay? So let us pre-multiply Klein equation by psi star into Klein-Gordon equation, okay, and subtract from it, okay, psi Klein-Gordon equation star. Okay, so I'm considering this relation. Now, I want to form this quantity. Let us see. Okay, so it will be psi star. It will be psi star. Okay, then del mu plus mc. See this mc square, mc by h cross c square, mc by h cross square will cancel out if I subtract this, because psi star will come here, psi star psi this minus psi star psi this, because this is real quantity. Okay, so I will not write this quantity here. Okay, so I will get from the first term I will get this minus from the second term I will get this. This is equal to 0. This implies, okay. So what I will do now, okay, I will throw this derivative, I will throw this derivative to the left of this, okay, and I will get a total derivative term and a term having the derivative on this. Correct? If I use chain rule, if I use your total derivative rule, okay, so del mu acting on psi star del mu psi will be del mu psi star del upper mu psi, okay, plus psi star del mu psi. Okay, so psi star del mu psi will be total derivative minus derivative this term with and derivative acting on this psi star. Okay, but I will have a similar term here, del mu psi and derivative acting on del mu acting on psi star. So I will be having terms like this. From this I will be having del mu psi star del mu psi. Okay, and from this I will be having del mu psi, okay, del mu psi star. Okay, clear? So this will come with a minus sign for this term, and this will, since there is a minus, this will be plus here. These two terms will cancel each other. So what remains here is del mu psi star, only total derivative terms will remain. Del mu psi star del upper mu psi minus psi del mu psi star equal to 0. Is this clear? Is this manipulation clear? Okay. So you convert this into a term plus a total derivative term. That the term apart from the total derivative term will cancel with this term. So I will have two total derivative terms. Okay. So suppose if I multiply this equation, this is for convention. This is the following step is just to bring your usual current density. You must have realized that I am deriving the current density, okay, charged and current density, as in your Schrodinger equation. Okay, so if I multiply this equation by factor I h cross by 2m, I multiply this just to match with your usual expression, usual non-relativistic current density. Okay, so I multiply this. After multiplication, what I will get is del mu, okay, I h cross by 2m, okay, psi star del mu psi minus psi del mu psi star, and this is equal to 0. Okay. So suppose if I name this quantity as J mu, if I call this quantity in the curly bracket as J mu, okay, so this quantity is 4 current density. And this equation tells us that it is constant. I have 4 divergence of that 4 current density is 0. Okay, is this clear? This J mu will have 0th component and spatial component, where J0, now let us calculate what is this J0. J0 will be I h cross divided by 2m psi star del 0 psi minus psi del 0 psi star. So this is, so if I express in terms of t, okay, so if I express this in terms of t, then it will be I h cross. So in fact, yeah, correct. So if I express in terms of t, then it will be I h cross by 2mc psi star del t psi minus psi del t psi star. Okay, clear? So your rho is basically this is the one factor of c which is coming. Let us see. Factor is coming. Just a second. So let's see. I want one more factor. So c times rho. Yeah. So this seems correct relation. Correct relation. Okay. And your vector j will be spatial component of this. Okay. So vector j will be, so there is a psi star. Yeah. So let me see. So it will be I h cross divided by 2m psi star. Now I want to write this in the vector form. Okay, spatial component. So there will be del I and there will be del I. J I will be. Okay. But del I is minus of your gradient vector. Okay. So this will be equal to minus gradient psi, okay, plus psi gradient psi star. Okay, so this will be equal to h cross over 2mi, h cross over 2mi psi star grad psi minus psi grad psi. Okay, so this is your free current density, and this one can write, now I can write this J mu as J0 and J, which is C times rho. Okay, so this I will call as, apart from this factor C, okay, I will call this as C times rho. Okay, and this is J, where rho now is h cross over 2mc. Okay, J0 is this. Okay, so h cross over 2mc, I h cross over 2mc. Okay, psi star del t psi minus psi del t psi. Okay, any doubt so far? So this is the usual thing. I'm following the same process as you have, as you must have done for Schrodinger equation. There is no difference at all. Okay, any question so far? Any question? Everything clear?
Sir, this J0 component, this J0, where we are expressing it as 0. So previously we got J0 as IH cut by 2mc into this current density, this psi star del t psi minus psi del t psi star. So when we are doing this, sir, in the last,
at this page?
no sir, next page.
Next page. Okay. So J0 is IH cross divided by 2m. Del 0 by C. Del 0 psi. Okay, minus psi del 0 psi star. Okay.
Yes, sir. In this line only, sir. This is my expression for J0 component.
J0.
Now when
J0
yes, sir. Now when we are considering this J0 component as some C rho, so this rho must be IH cut by 2mc square, right?
Yes. Okay. Yeah. Sorry, because there is a C. Right. Correct.
Sir, then this rho is my dimensionless quantity.
Correct.
Oh no. Sir, what is this significance of this rho here?
So I will come to that. What is the significance of this? I will come to that.
Okay.
Okay. So till now we are progressing along the same route that you would have taken if we would have the Schrodinger equation. Okay, exactly the same process you do. Okay. Yes. So I should write here J. So J is this. Okay. So you have rho and J. Now, can someone tell me what is rho in Schrodinger equation? For Schrodinger equation, what is rho? Just tell me.
Probability density.
No, but what is the expression?
Psi star psi.
No, there are some factors, right? There will be some H cross, something, some factors will be there, right? Okay, so let us see. Psi star. Psi. Now, what is the essential difference between this and this? So I want to interpret this as my probability density. But you see, I cannot, because this, if I want to interpret this as a probability density, it better be a positive definite quantity. Okay, probability is a positive definite, so probability density is a positive definite quantity. But you see, I can adjust this psi in such a way that this term exceeds this term. Okay, so there is a balance between this term and this term. Okay, I can choose my initial conditions. Okay, is this point clear? That this quantity may exceed this quantity. Is this clear? Okay, so this could be in principle negative quantity. But even if I set this quantity less than this quantity, okay, suppose if at time t equal to 0, okay, my psi at time t equal to 0, my psi and derivative of psi at 0 are such that this quantity is positive definite. Okay, okay, but there is no guarantee that as time evolves this remains positive definite. There is no guarantee at all, because at one time, if I set this at one time, okay, such that this is less than this, okay, as time goes on, okay, I can have the size such that this exceeds this at some time, at some later time. Okay, is this clear? Okay. So I cannot interpret this quantity as the probability density, and that is the main problem with the Klein coordinate. You cannot interpret this rho as probability density. But let us see what it gives. Okay, so if I use this current conservation equation, del mu j mu equal to 0, and if I write it in the what? Okay, so if I write it in explicitly component form, what I will get? Del mu j mu equal to 0 implies del 0 j0 plus del I ji equal to 0. This implies, okay, j0 is so this I will get 1 over c del t of j0, but j0 is 0, so it will be this quantity I h cross. So yeah, so I will write it now. I will write 0. Okay, so this c will come here, it will cancel, and I have rho plus del I ji. So that is del dot j. This is 0. Okay, so I have continuity equation. The continuity equation is satisfied. Okay, but I cannot interpret this rho as the probability density. Okay, so if the continuity equation is satisfied, then I can integrate. Suppose if I integrate on both sides over a space, over a spatial volume. Okay. This will be minus d3x del dot j, right? Okay, so this implies del t of d3x del d3x and rho. It is a function of placement time. Is equal to minus. This will be, so if I use this Gauss law, okay, so this will be dx some spatial surface normal to it dot j. Okay, so the integration will be on some spatial boundary. Okay, so this is equal to, okay. Now suppose if I assume, see, J consists of what? J consists of this psi and psi star. Okay, psi and derivative of psi. Okay, and also derivative of psi star. So you have psi star, derivative of psi, and derivative of psi star. Okay, spatial derivatives. Okay. Assume that this psi goes to 0 at spatial boundary. Okay, this usually we assume that always. Okay, so under that assumption, since J contains psi and its derivative, this will go to 0. 0 by assumption. By assumption about psi on boundary. Okay, is it clear? So I have, since I am integrating this quantity over space, so this will be a function of time. So I can replace this by total derivative. So this will be d dt of q equal to 0. Okay, so I have conservation of charge, okay, where q is integration, spatial integration of density. It is some sort of density. So I have the conservation of q, namely the q at one time is same as the q at another time. But I cannot interpret this q as q is not probability density or probability charge. Or total probability, or maybe total probability, or whatever you say. Okay. Namely, so now normally we call total probability as number density, right? Okay. So this Q is not number density. It does not represent number density because number density cannot be negative. Okay. But this quantity may be negative. Because this quantity may be negative. Okay. So I cannot interpret this as the number density or total probability. Okay. But this Q may represent some charge. Some charge. I don't know what this charge is. Later on it will be clear. Okay. Is this point clear? So the first difficulty is, okay, first problem with the Klein-Gordon equation is that psi dx cannot be psi dx not psi dx. The difficulty in interpreting rho. Okay, it is the first problem. Okay, is this clear? Yeah. And that problem is expected because this is the second order equation. It must have two initial conditions. Okay, this is second order equation. Okay, in time. Okay. So you have to provide two initial conditions. Okay. While the Schrodinger equation is first order differential equation time, it only has, you have to give one initial condition about psi, not about its derivative. Okay. Yeah. So all the problem is, this problem is occurring because of this relation. Okay. Right. So we cannot interpret this rho as the probability density. It is the first problem, okay, with Klein-Gordon equation. Okay. Now let us see what kind of solutions I would get for this free Klein-Gordon equation. What kind of solutions I would get for this free Klein-Gordon equation? Okay. To see that, okay, I can write this box plus mc by h cross t square psi equal to 0 in slightly different way. Okay. What is this box represent? This box represents 1 over c square del 2 by del t square, okay, minus gradient square. Okay, this will act on this psi. Okay. What is this gradient? Okay. If I want to write as you write Hamiltonian, usually in your non-relativistic quantum mechanics, you write Hamiltonian as T operator square divided by 2m, right? Okay. Suppose if I write this as in the following way: 1 over c square del 2 by del t square, okay, minus, it is minus minus plus, so I will write this as, so I want to write minus I h cross minus I h cross, so I square, so I write plus here, I will divide by h cross square here, and I will write this here. Okay, this will act on psi. Oh, there is one more term, so this plus mc by h cross square, so there is a plus mc by h cross square psi equal to 0. What is this? I can interpret this as your momentum operator, okay, because minus I h cross gradient is your momentum, so it is p square, basically p square of over h cross, okay, this entire quantity. Okay, fine. So I have 1 over c square del 2 by del t square plus p operator, so this is a vector operator, square divided by h cross square, okay, plus mc by h cross square psi equal to 0. Okay. Now suppose if I see this equation in the rest frame, what do you expect? In the rest frame, what changes do you expect? Suppose I have a rest frame for that particle. That means I am on that particle. With respect to rest frame, there will not be a momentum. So there is no point in talking about this term. Correct? So in the rest frame, I will have something like this. I will have del 2. Okay. Firstly, in the rest frame, tell me the dependence on psi. Since there is no momentum dependence, since the particle is not moving, okay, there is no need. Psi at x equal to 0 is same as psi at x equal to say x, because particle is not at all moving. Okay, so this will be psi at x equal to 0, and so first of all I will write this wave function as psi at x equal to 0 and t. That is sufficient, because it is as good as writing psi at any arbitrary x, because particle is not at all moving. Okay. Consider, so there is so there is no point in writing x here. You can write, but that x is any x. You can take any x. Okay. So in the rest frame, we will be having the following equation: d2 by dt square. Okay. So this c square will make it c to the m square c to the power 4 divided by h cross square, minus or plus m square c to the power 4 divided by h cross square. Okay, psi equal to 0. What are the solutions for this? What are the solutions?
Sin
dt
and
psi
cos.
by dt. Yeah, sin and cos are in general. You have
E raised to
sin
I
and
kx.
into the power k. See, you have psi at 0 and t. Okay, what will be that k? If you're saying that kx, what will be that k?
Omega.
It is,
Omega.
but what is that? But what is that here? This will be square root of this quantity, right? That will be
MC
your
square
omega.
by h.
So this will be e to the power plus or minus plus, okay, IMT, right? IMC square t by h cross square. IMT c square by h cross. Correct? Sorry. IMC square t by h cross. Square root of this. This will be the solutions. There will be some normalization constant. Clear? You will have positive as well as negative. Okay? But these are the solutions in rest frame. Okay? Clear? Okay. So let us write that as phi plus 0t as n e to the power minus I m c square by h cross t, and psi minus 0t as n e to the power plus I m c square divided by h cross t. So you have two solutions. Okay. Is this clear? And now I want, my aim is to get the solutions in any arbitrary frame. So I will see here psi is your scalar. Psi is a scalar. Okay. It has in rest frame, it has this form or this in rest frame. Okay. I want to get psi plus and psi minus in any arbitrary frame. moving with velocity v, okay, with respect to rest frame. Okay. If I achieve that, okay, that would mean that I am representing a particle from a frame in which that particle is moving with some velocity, classical velocity, right? So I will be obtaining the wave function for a particle, okay, which is moving with, say, classical velocity v, free velocity, okay, with respect to some fixed frame. Clear? Okay. So how to get that? Remember, this is your scalar function. This is Lorentz scalar. Why this is Lorentz scalar? Because this quantity, see, this quantity is Lorentz scalar. Okay. So this better be a Lorentz scalar. Where that argument is not enough, because I could have taken here vector field. Okay. But here I am talking about the scalar field or scalar function. Okay, that is by assumption. So I have taken the scalar function. I could have taken vector function. Okay, but at the beginning we will consider the scalar function. I will discuss the transformation properties of this psi, or in general the scalar field, okay, later on. Okay, but this is your Lorentz scalar. Okay. And it has this form in one frame. So what do you expect in other frame? See, you concentrate on, okay, let us concentrate on this factor. Okay. In this factor, mc square over h cross t. Okay, this I can write as c square by h cross. There is no problem with this. Okay, I have mt here. You must have guessed that this mc square is just a rest energy of the particle. So I'm writing in this form. Okay, this I can write as this will be, okay. So this I can write. This thing is nothing but, let me write it properly. Okay. So this will be m. So this will be, okay. So let me write this quantity as, this is your rest energy, E rest, ER or E rest. Okay. If I multiply by C here, there is no need of doing that, but let us do that. Okay. If I'm okay. So in fact, there is no need of considering H cross also. Let us consider just mc square t. So if this mc square is your rest energy. If I multiply by C, then I will divide by C, and T is there. Okay. What is this? This quantity is P0. And I have T. Okay. And this factor is coming as an argument of some Lorentz scalar. Okay. Clear? In any other frame, okay, so in the rest frame, if I want to write, this will be C times, okay, I can write this as P mu x mu, okay, where my P mu is m 0 0 0 and x mu is t 0 0 0. Okay, then P mu x mu will be empty, just okay. Okay, because why I wrote that? Because I know that this is the zeroth component of 4 coordinate vector, and this is zeroth component of 4 momentum. Okay. Okay. So I write this in this language, okay, where p mu and x mu are this. Why? Because we are in the rest frame. So rest frame, all the coordinates we are at the origin. So I set x, y, z to 0.
X mu will be only T00 or CT00.
X mu will be, yeah, CT00. Yeah, because there is a C here, so there will be CT00. Yeah, X mu will be just a minute. So T, CT, yeah. So there is no need of writing C here. Okay. Clear? So I have something like this in this exponent. Let us consider now e to the power minus I mc square t y h cross. Okay, this is equal to e to the power minus I. Because of this, I can write this as e to the power minus p mu x mu by c by h cross. Okay. But now you see this quantity is Lorentz scalar. Whether I evaluate this quantity in rest frame or in any other frame, any other inertial frame, it doesn't matter. This value of this quantity is not going to change because this is Lorentz scalar. Now, okay, so this is equal to, let me call, instead of p mu x mu, let me call this as p prime mu x prime. Okay, and this will go to in any other frame. This will be equal to p mu x mu. Okay, where my p mu is E by C and P, and this E is m gamma C square. Okay, this is not the rest energy now. This is total energy. Okay, so now I am going in the frame which is moving with velocity v. Okay, clear? Is this clear? So this quantity will transform to e to the power minus, so this will be prime. So this will transform to e to the power minus I h cross p mu x mu, where p mu is this and x mu will be some coordinate time. So maybe you can use t prime here. There's no harm. Okay, so this will be some coordinate time, and I have some x c. Okay, so I have generated a function from the scalar function in the rest frame. This is also scalar. Okay, so how I generated that? Okay, I note that mc square t is nothing but p mu x mu, p prime mu x prime, where p prime is this, okay, a particular 4 momentum. A 4 momentum in the rest frame will take this form. Okay. Okay, so there will be some factor of c still missing. Okay, so I have to multiply here by c here. Yeah, so e by c is e0. Okay. So e0 is mc, correct. Okay. Now, if I have the form of a function in the rest frame, how to get a function in any other Lorentz frame? Just to consider the Lorentz transformation. In this case, that Lorentz transformation is a boost. in any arbitrary direction. Even the form of that Lorentz transformation is not required. We just have to note that this quantity will be invariant under Lorentz transformation. P prime mu x prime mu will be same as P mu x mu, where P mu is now general 4 vector, 4 momentum, okay, and x mu is any general coordinate vector. Okay, so from the rest frame, so I have the rest solution. I have the solution of Klein-Gordon equation in the rest frame. Now I have obtained a solution which holds in any frame. That means this will be a solution for this, a solution, because I have taken only minus here. There will be a plus another, but that will be the same. Just I will. So this implies that e to the power minus plus I mc square by h cross t is equal to e to the power minus plus I by h cross t mu x. That's it. Okay. So I have the solution for the Klein-Gordon equation. Okay. So psi at time t and any x will be some normalization times, so psi plus some normalization times e to the power minus I p mu x mu. Okay. This will be equal to by h cross. Okay. So this will be equal to some factor of c. I did some mistake. There is a factor of I think there is some factor of c which is missing. Okay, let me see. So c times t0. Okay. So mc square is mc square t is c by c e raised. Just a minute. I will call just a minute. Hello. Yeah. So there is some factor of c is missing somewhere. Okay. There is c times t is x0. Okay. So ct is x0. So this will be p0 x0. Okay. So that I can write as p mu x mu. Correct. So this fine. Okay, I think everything is okay here at least. Okay, so this is equal to I want to write it in terms of energy and So I can write this as e to the power minus I by h I. Okay. So this will be P0 x0, that is P0 is E by C, x0 is Ct, so this C will not be there. Okay. So there will be T, Et minus Pi xi, so that will be P dot x. This minus sign is because we have lowered, okay, or we have raised this x lower I to x upper I. Okay. So this will be one solution. Another solution will be x minus Tx is equal to normalization e to the power plus I Et minus P dot x. So I have two solutions for the Klein Gordon equation. And let us see what this equation gives us. If I act IH cross del del P on psi plus, what I am going to get? Minus I will give me, there is a H cross here, minus I, so I will get plus H cross, this H cross will cancel with this H cross, I will get E times psi plus. Okay, and if I act IH cross del on psi minus, what I am going to get? I will get minus E psi plus. Sorry, psi minus. Okay. Where now here when I use this relation, is E is positive square root. Okay, remember you go up to our earlier lectures, this E is positive square root. E is vector p square c square plus n square c to the power 1. That is positive square root. Okay, so this E here is positive quantity. This E is always p square c square plus m square c to the power 4. Okay, but when I add this del IH cross del del T psi plus, I will get E psi plus. That means this gives me positive energy, E. But when I add IH cross del del T on psi minus, I will get minus E. Okay, is this clear? Hence, I have this psi plus represents positive energy solution, and psi minus, okay, represent negative energy solution. Is this fact clear? This E is positive here, always positive. Any question so far? So we are discussing the free particle solutions, free solutions of Klein Gordon equation. Sometimes it is called plane wave solution. So these solutions, okay, sometimes it's called psi plus, psi minus, are called plane wave solution. Because of the nature of the phase factor, P Et minus P dot x. So that phase is constant on plane. So it's called a plane wave solution. Okay. Any questions so far? So we generalize the Schrodinger equation. Okay. We constructed the relativistic generalization of Schrodinger equation. We observed that it satisfies the continuity equation, but the density, the zeroth component of 4 current density is not necessarily positive definite. So I cannot interpret as a probability density. It could be certain charge density. Okay, that is the first observation. Then we solve this Klein-Gordon equation, and the conclusion is that we have two independent solutions representing the positive and negative energy. And this fact is distinct to relativistic systems. Okay. This fact is quite distinct from your usual non-relativistic Schrodinger equation. You always get positive energy solution. Okay, and you can trace back the problem to this. You can always trace back to our starting point. This relation. Any questions so far?
Sir, is psi minus physically possible? Because
Yes, yes.
if the particle, if the particle is not under any potential, then the total energy must always be positive. So,
yes, but no, but that is classical statement, right? In quantum mechanics, who knows? Like we are in the unknown territory now. Okay, we are just following the. We are taking into account the principle of relativity and applying them to quantum mechanics and trying to generalize the Schrodinger equation. We are getting whether it is physically possible or not, that is a different issue, but we are getting two solutions. Okay, and I cannot discard this solution. Simply I don't like, I cannot discard this. You will see that later on, even if you discard them, they will come again. Okay, you consider a linear combination of psi plus psi minus, okay, and construct a psi. Now you choose psi such that the psi minus is not there. The coefficient of psi minus is not there. If you time evolve, that coefficient may not be 0. Okay, so you cannot just discard them. And you will see the later on what is the physical interpretation of those solutions. Okay, so as it stands, we have this problem of negative energy solution. Okay, so now we have positive as well as negative energy. So as a result, how this Klein-Gordon spectrum will look like? Energy spectrum. Or I don't have to write energy since I'm writing spectrum. Okay. So you have this as an eigenvalue of del T. Okay. So this is my energy. Okay. And what is E? E is square root of P square C square plus M square C to the power 4. Okay. So what is the lowest positive value? So let us concentrate on positive energy solution. Okay. What is the lowest value? Okay. So what is the lowest positive value of energy, of positive energy? MC square. That is lowest positive value means I have to put momentum to 0, right? Here. So if I put momentum to 0, I will get E equal to plus M square MC square. So that is the lowest positive value. Okay. So I have a level here. Okay. And above that, since P takes continuous values, okay, I will be having continuous levels. So this is MC square. Then I will be having continuous levels for different p, and so on. Okay. Similarly, I will be having negative, least negative value. Okay. What will be the least negative value? Minus m square, mc square. Okay. So it will be minus mc square. Okay. And then again I will be having continuous level below that. And so, okay. Now you see the big problem. The big problem is not the value of energy is negative. The problem is that I have a negative and then I have indefinite negative states here. It will go till infinity, right? What is the problem then? It means that we do not have ground state, right? There is no ground state now. You can, it's indefinite. You can go till infinity. There is no lower bound. See, ground state represents the lower bound of your spectrum. Okay, any state could be higher than the ground state. Okay, and there must be a bound on the ground state. There must be the bound on your spectrum. That bound is called ground state. Okay, otherwise there will be several problems. Your norm will not be positive and so on. That we are seeing that norm, the probability density is negative. One of the reasons is this, that your bound on the states, this state will be in some Hilbert space. Okay, that Hilbert space will not have the lower bound. The Hilbert space of states, if I consider the Hilbert space of states, then that space will not have lower bound. Okay? Is this clear? That is the big problem. And there will be excited states here. But these are okay. There is no problem here because we don't expect any upper bound on the states. Okay. But there must be, if it is a valid quantum system, then it must have lower bound. The states, the spectrum must have lower bound. That lower bound we call as a ground state. Okay. So every quantum system must have ground state. Okay. But here what we are saying that I can go till infinity. Infinitum. Okay. And hence I don't have any state. I don't have any ground state. Okay. That is the big problem. But still, this equation has some success stories. Okay. For example, one can interpret this psi as a wave function for pion. Okay. If you know, there are pi plus particle, pi minus particle, and pi zero particle. Okay. So this pi plus represents the positively charged spin zero particle. Okay. And the psi may represent the wave function for that particle. Okay. So I can consider in fact a pionic atom. Okay. So I have two pions, and instead of proton and electron, I have pi plus pi minus. Okay. And they form a bound state. Okay. And if one calculate the you go with the same route as your Schrodinger case. In Schrodinger equation, how you approach the hydrogen atom problem? Okay, you construct the radial equation, you solve it, okay? You will have some series solution and so on. So you will get, ultimately you will get energy levels. So here also you apply the Klein-Gordon equation to pionic atom. Okay. Okay. I cannot apply this to electron. Why? Because this wave function is not, it has a spin 0. It is appropriate for spinless particles, and pions are spinless particles. So if I consider the pi plus pi minus system, bound state in the bound state, it will mimic hydrogen atom kind of situation. So it will call pionic atom. And you calculate its energy spectra. Okay. It will give us whatever is expected from Schrodinger equation. Suppose if I consider the pionic atom and apply Schrodinger equation to that. Okay, so I will get some energy levels. Now if I apply Klein-Gordon equation to that pionic atom, okay, I will get some energy levels. Okay, so the energy levels obtained by Klein-Gordon equation, okay, gives us the correction to the energy levels obtained by Schrodinger equation. So that corrections are basically coming from relativity. Okay, so those relativistic corrections will be taken into account. Okay, if you apply this Klein-Gordon equation to pionic atom. Okay, but the main problem remains. Okay, so you have that probability density problem remains always. Okay, and where for pionic atom, this kind of situation will not arise because we will be having bound state, so there will be some potential. Okay, you will get some corrections which are worthwhile to study. Correction to what? Correction to answer coming from Schrodinger equation. Okay, that I will give as a lab exercise in your next semester. Okay, there is a big, you have to apply Klein-Gordon equation to pionic atom. You have to solve radial Klein-Gordon equation, and there will be you have to study in detail the radial Klein-Gordon equation. That I will give as a lab exercise for in the next semester. There will be special lab associated with the special subject. It's called special lab. Okay, so in the lab I will give that as an assignment, okay, as one experiment. Is this clear till now?
Sir, suppose the particle is at rest, then also here he has two energy possible, mc square and minus mc square. So how can it be one particle has two eigenvalues?
No, I'm having two solutions, right? I have a that means, see, the problem is that I have to interpret somehow. I have to interpret these negative energy levels. There is the interpretation. There is some interpretation to these energy levels. They are not that much ad hoc. Okay, there will be some interpretation. Some interpretation will be given to these energy levels.
Sir, according to this
So
new interpretation.
Just a minute. Let me complete. So I have the energy level for. I have the positive energy spectrum. I have negative energy spectrum, which is allowed by the Klein-Gordon equation. I am not saying that one particle simultaneously will have this and this, the positive energy as well as negative energy. Okay. Given a particle, it will either have positive solution or negative solution. But negative energy solutions are possible. That is what I am saying here. Okay. And because of that, there is no bound on your state space. So when the particle is at rest, you have only two levels. Two levels are possible. Okay, particle will occupy either this or this. Okay, now you add these levels. Then the particle will occupy this infinite state, or one before that, or one before that, and so on. But the fact that there are infinite, there is no bottom to this, okay, says that this system is unstable. In the sense that there is no bound, lower bound on it. Yes, there was second question.
No, sir. My doubt got cleared actually while you were explaining right now.
Okay. Okay. Any other question?
Sir. Sir, here we are having certain energy gap between the positive energy solution and the negative energy solution.
Yeah, yeah.
So is it if I have a solution that is superposition of both the states, then can my energy be in this energy gap?
No. It's not like that, right? Because see, it's not. No. If you consider the general solution, let us go to this. That I will do eventually. Okay. So if you consider a general solution psi, which is linear superposition of psi plus psi minus. Okay. It is not an eigenstate, right? It will not be your eigenstate. Okay. So this will represent e to the power minus I p mu x mu. Okay. With some linear combination, say that linear combination a p, and this will be some dp. Okay. A p e to the power minus I p mu x mu plus dp, okay, e to the power I p mu x mu. This is what you are talking. Am I correct? Okay, I am considering the particular linear combination of positive as well as negative energy solution. Okay, but this is not a definite energy state, right? You consider a particle in a potential well. Okay, what is your ground state? Okay, it sine n pi x, so pi x by L. Okay, then what is your first excited state? Okay, sine 2 pi x by L. Okay, the psi, which is 3 times psi 0 plus 4 times psi 1. Okay, H acting on that is not energy. This is not the energy eigenfunction. There is no meaning, right? Is this clear? Why this is true? Because H acting on psi 0 will be E0, ground state. Okay, 3 times E0 psi 0 plus H acting on psi 1 will be E1. Okay, psi 1. Okay, you cannot. This is not equal to some number times this state. Right? So this is not the eigenvalue equation. This psi is not eigenstate of H. So linear combination of two energy states is not necessarily an eigenstate in general. Okay, so there is no question of having the energy in that gap. It's not like that you superimpose, you will get the energy between the gap. That is not true. Clear?
Yes, sir.
Any other question? What is the time? So 4 o'clock. Any other question? Okay. But you will see that some interesting thing can happen if I construct a similar wave equation for electron, that means for spin-half particles. Okay, there is some escape route from this statement, and I will tell you the answer before I get into that. Okay, suppose if I have electrons, suppose I have equation representing the relativistic electron, and suppose if I obtain some similar spectra, okay, then the escape route is because of the Dirac, okay, because of his ingenuity. What he thought was the following. Okay, suppose if you have this kind of spectra, although it is unbounded from below, I can fill these levels by electrons. Okay, I can fill these levels, okay, completely. So suppose there are two electrons here, one spin up, spin down, then spin up, spin down, spin up, spin down, spin up, spin down, spin up, spin down, and so on. Once I have two electrons here, I cannot put more than two electrons in one state because of Pauli exclusion principle. Okay, in one state I have only two electrons, spin up, and spin down. Okay, so next two electrons will sit in the next energy level, and so on. Okay, yes. In that way, I can fill these levels till this minus mc square. Okay. And then this entire thing will represent a ground state. Okay. Is this clear? Okay. That this is the genius of Dirac. Okay. He thought this problem in different way. Okay. You fill these levels by two electrons, then two electron, and two electron, and so on. Ultimately, what will happen? It will go till here. Okay. And after that, okay, you cannot have any negative energy vacant state. Negative energy state that is vacant. All are filled. Okay. So now electron cannot go here. Okay. I cannot do this for spin zero particle. Why? Because all the spin zero particle can sit in this state because they are bosons. Can sit in this infinitely bottom state. But these are infinite states. Okay. So there is no meaning to it that boson will fill these energy levels. They will never, because if I give you unlimited amount of bosons, okay, they will come and they will sit here. Still these states are vacant. So next boson will come and go down, and he will also go here. So you cannot, for bosons you cannot use this picture. Only for electron one can use.
But sir, if there is no lower bound, then electron will go down and down and down.
Yes, but no, but down and down, but whatever that infinitum states, okay. Once you fill with the two electrons, okay. Suppose if I have a hypothetical state, okay, which has infinitely negative energy, okay, I fill that electron, I fill that state with two electrons, okay. Okay? Remember, this is the state having infinite negative energy. Okay. So I assume that this state is filled with two electrons. Okay. Then the next electron, third electron, will never go to this state. He will go to this state. Okay. He will sit here. Next electron will come and sit here if its spin is opposite to this, and so on. So in this way, I can fill it. Okay. I cannot do the same thing for bosons. Is this clear? But inherently then, even if with the Dirac's conjecture, or even if with this Dirac's thought, there is a problem. What is the problem? That negative probability density, that problem, okay, that problem is also can be tackled. But now the problem is you started with one particle quantum mechanics. You started with one particle quantum mechanics, and you ended up with many particle quantum mechanics, because now you are bound to assume the existence of many electrons which are required to fill this. So when you start discussing relativistic quantum mechanics, it no longer remain a single particle picture. Okay, you are bound to discuss many particle physics. But at least at intuitive level, the Dirac proposal works. And in fact, it works. It predicts positron and so on. Okay. Okay. But the way Dirac did will have some problems. Okay. But ultimately, the physics level, it's sorted out at the physics level. Okay, all these levels are fulfilled. Okay, so one can assume this itself as a ground state. So the ground state will be having infinite number of electrons. Okay, so that's it. Once you have that, then you redefine the state, ground state, as the collection of these infinite number of electrons. The next electron will definitely go to positive. So you say that my system consists of these filled levels and then these unoccupied levels. That will be our starting point. So that is the escape route which Dirac gave. And in fact, through this Dirac predicted the positron, and it conforms with the experiment. Okay. But only the pedagogical problem is the following. You started with the single particle equation, and you ended with many particles. That is the main problem. How to reconcile this? Okay. So for that we require quantum field theory. Single particle interpretation is not sufficient when you take into account relativistic effects. You are bound to get many electrons or many particles. Okay, but this we'll discuss when we come to Dirac equation. Okay. But before that, there are other interesting solutions, other interesting scenarios that one can discuss with a Klein-Gordon equation. Okay. Fine. So. Yeah, so one can write, so we have derived the expressions for rho and free current density, G, vector G. Okay. Rho and G. This is rho and G. So I will give you the following exercise. Calculate rho and J for psi plus Tx and psi minus Tx. So you will get two expressions, rho plus rho minus, J plus J minus. Okay, so you get, this will give you rho plus rho minus, J plus J minus. Okay, then so this is the first thing. Second, okay, concentrate on positive energy solution. Take positive energy solution. Okay, this implies you take only psi plus. Okay, and then you have rho plus, corresponding rho plus. Okay. Now you discuss the non-relativistic limit of rho plus and show that in the non-relativistic limit, rho plus goes to psi star psi. Okay, there. And third part is that discuss the relation, not in the non-relativistic limit, in general. Discuss the relation between J plus Tx and J minus Tx. Okay, so this is one exercise. So it is in the order. Okay, it's a very simple exercise. Okay, you have everything. Okay? You have the expression for rho and J. Just substitute these forms. Okay, these solutions here, psi plus and psi minus. Okay, in the expression for rho and J. Okay, so you get rho plus rho minus, J plus J minus. Concentrate on rho plus. Okay, and take the non-relativistic limit. You think how to take non-relativistic limit. Think before taking this non-relativistic limit. You have to be careful. And show that this rho plus indeed goes to your usual probability density. This is your usual probability density. Okay. Then next, discuss the relationship between J plus and J minus. Okay. So you must have obtained this. Okay. Then use these two and discuss the relation between them. So this is the exercise. Okay. Fine. So I think I will stop here. So because it's 4:20. In the next class, we will discuss about how to introduce the electromagnetic interaction into the Klein-Gordon equation. Okay. So I will take the next class on most probably on Monday. Okay. So Monday when you have the exam? Hello? On Monday when you have exam?
3 to 4:30.
3 to 4:30. And it is ED2, right? So everyone will be there. So next exam is for you or for other people? Next exam is of which people? Next exam is
It's not for us, sir. Crystallography.
crystallography, right? But crystallography, this thing, what is the subject corresponding to crystallography? STQM, right? STQM is not on that day, right?
No, sir.
Okay. So I will take on Tuesday. Okay, because Monday you will be having paper, so I will take on Tuesday. Both MMP2 also I will take, and I will take a advanced quantum EQM lecture also. Okay. So if you have any question, you can ask. Okay. By the way, so the reference for this from now onwards, I will be using. Okay. The reference. So I am not following any one particular reference, but you may use advanced quantum mechanics by J. Sakurai. Okay. Then there is an excellent book by Franz Gross. You can use that. And third is again it's all-time classics. It's called Shorkan and Trail. So there are 2 volumes of Jorkan and Trail. Jorkan and Trail, Relativistic Quantum Mechanics. Okay. And there is another volume, this is volume 1. There is another volume, Relativistic Quantum Fields. So you can use this reference. You can use first volume. So mainly these are the 3 books. Okay. But there are other references also, so I am not following any one particular. Okay. About this advanced quantum mechanics, Sakurai, okay, he uses metric in slightly different way. Okay, he uses ds square as ICT square kind of. So instead of CT, okay, CT and X, he use ICT. Okay, ICT. Okay, and for a metric he used dt square plus dx square plus dy square plus dz square, or dx0 square plus dx square plus dy square plus dz square. But then dx0, because of this I, square will become minus. So ultimately it will become same, but he uses this as the way. It's not good way of writing. It is an old-fashioned style. It is an old way of writing this Minkowski metric. Okay. Apart from that, there is no other thing. Ultimately, it will not create any difference. Okay. Physics is extremely good. Okay. So these are the references. If you have any other question, you can ask. Otherwise, I will end the meeting.
So syllabus for internal.
Syllabus for internal, as I told you, right? Syllabus for internal, whatever I cover till the your internal exam. Okay. So please start studying. I think you must be studying. Okay. So it's not that I will give the syllabus till today. It's till the internal. Okay. Whatever I take, maybe to suppose if we end the class on Tuesday, so syllabus till Tuesday. If I end the class one day before the exam, the syllabus will be one day that syllabus. Okay. So for that, you should be clear in your understanding about past lectures. Okay. And it is logical that I'm not going to give so much weightage for the last day, for the syllabus which I covered on last day. Right? Okay. But if you ask syllabus, it will be one day before whatever the class, whatever we finished before the internal. Okay. And okay, so I want to mention few things here. Okay, so